given the root of the binary theorem, it's a valid binary search. So not sure if you're familiar with binary search tree. Binary search tree is all the left node is should be less than the right. Yeah, basically 1, 2, 3. 1 should be less than the middle node, and then 3 is greater than the middle node. So if you have something like this, 1, 5, 4, 3, 8, 3 is less than 4, but 6 is greater than 4. What you'll notice also is all of the nodes on 4, 3, 6 are all less than are all greater than 5. So the one in the middle should all the nodes greater than the middle should always be uh, greater than the uh, all the right nodes should be greater than the middle node, right? Even the children. Yeah. So common misconception of like trying to solve this problem is like what you're doing is only taking note of this left and right node. So if 3 is less than 4 and 6 is greater than 4, then you're saying it's valid, right? But actually that's not how this problem works. um, because it's possible that the node on the top of them, the parent node on top of them, is actually less than 4. So if you have let's say you got an example. I'll probably show you an example here. So a possible tree that can be broken is yeah. So everything here is should be greater than 6, but it's possible that you have somewhere in the middle of like, okay, let's say you have a 7 here and then you have a 6 here, and this is not considered valid because 6 is less than 7. So this is actually a invalid node. But if you do this algorithm that in the middle, you just check the middle one, like 6 is less than 8 and 9 is greater than 8, then you say it's valid, then it's not going to work. This is a failed solution. So the thing that you really need to compare here is it's not really the two nodes of between left and right, but it's actually the last two nodes, the last two parent nodes. So in this case, like 654, just looking at this tree, 654, what you really need here is this and this. So you have to, let's say, change the color of this maybe. Let's just change the color of this. It's 2 green. So the right side goes like 6 goes to you go to the right, which is 8, right? And then actually this is 6. Your left now is 6 because it's on the left side of this, and your right is nil. Now once you go down the right path, so the right of 8 is 7, right? So this is 6. So now you're comparing the left here and the right is 8. So you're trying to like making sure that 7 is greater than 6 but less than 8, right? So this is actually what you're actually doing here. So this actually should be 4. Sorry, this is a wrong example. Sorry, should be 5. That's why it's wrong. So all the 4 should be replaced by 4, 5. You notice that this is your middle, right? 5 is greater than 4 and it's less than 6. So when you go to the right, what's happening here is, let's say 8. Now the right is 8 on the right is 9. You know there's a left node, but there's no right node because you're like on the edge here. There's nothing that is greater than this. So you just compare it from here. Yeah. So basically you need the last two nodes that you pass around, except from the edges. The edges doesn't have because the edges, like, you only have a maximum right, you don't have a left. Now this, like 4, 3, the max is right. Yeah, so that's how you actually solve this. So maybe we can go to the coding section. Yeah. Give it a little thought about this. Like, the way you solve this, you pass this 2, and then this becomes your left, and this becomes your right. The 4 becomes your left, and becomes your right. When you're going to the right side, it's the same thing. Like 6 becomes your left, 8 becomes your right. So basically, you're passing this current 6 existing 6 as the left will still be the left, and then you change their 8 as your right. Yeah. Okay, let's try to solve this. So yeah, you need 2 additional parameter, which is basically the left and the right, right. And then you do your usual check here. If root is equal to nil, it means you go to the edge, which means okay, we're free. It's true. It's clean. And then you do have these 2 conditions. So what you need to do is basically call left and call right. So when you go to the left, when you go to the left side, the left will still be left, but the right will become your root, right? And when you go to the right, this right becomes your root, right becomes your right. Yeah, let's just look at the example here. Like, okay, let's say I go to this side here, right? Okay, 4, 6 at this level. 4, 4, 6. So 6 is coming for the existing node, which is your right. And the left is still left, which is this. Left is still nil, right? On the other side, when you go to the right side, your current node becomes your right, your left, and the right is still right. So you're just copying the right. The same thing here, right? When you go here, 8 goes to the right, which is 9. 9, the root current left becomes the current node, which is 8. And then you just copy the right, which is nil. Yeah, you just copy the right. Yeah. But when you go to the left side, so 7 goes here, and then the backs node, which is the right of the left is actually the current node, which is 8. And then you copy the left is this. Okay, so basically you're copying left when you're going left, and you're copying right when you're going right, and then you copy the current node as a max, right? Or it's either left or right. So that's what's happening actually here. So the check that you need to do is if root.val, okay, let's say the left is greater than like val, then it's basically false, because the left should always be greater than right, right? The left should always be less than the right. Same thing with here. If root.val is greater than right.val, turn false. Now you can have a nil here, so you need to check if nil is not equal to nil, and because initially it will be empty, right? Right. Okay, so now we just call this method here root and nil. I'm starting with the empty left and right because you don't have a left and right. Two top nodes is empty. Just run it, see if it works. With the issue, syntax error. Okay, so in Golang you need to put braces. That's the thing you need to take note. Do a Golang, you always have to put a brace. Same thing here. Same thing here. Let's run it. 2 is not queues. Forgot the word return. let's just submit it. Wrong answer. Okay, so there's 2, 2, 2. So it's considering equal. So you need to make this less than equal, greater than equal. Okay, should return false because it's not a binary tree if there's an equal. Submit it back. There you go. Actually, I was able to run it 2ms, but sometimes the server is lagging. Doesn't really give you the like fast response. But yeah, basically that's how you solve this. The speed is like because you're traversing all the nodes. So I would say this is the number of nodes, which is n. It's basically linear, right? So basically going after all of the nodes you go one time. Yeah. So yes, this is how you actually solve this problem. If you like this video, please hit like and subscribe, and we'll see you again, right? The next session. Hope you enjoyed this session. Thank you for watching. Yeah, probably have a different kind of